Initial conditions have come up a number of times in the conversation so far, and I think this is a good time to bring up the role of entropy in life.
Yes. Yeah. So this is one of those interesting topics. I'm currently teaching general relativity and cosmology to my students, and we have to talk about entropy quite a bit, and it clearly is a very confusing topic. So there's a couple of key things with regards to entropy and the universe, which is strange. So we all have this sort of schoolbook picture of what entropy is, right? Something to do with disorder, something to do with messy bedrooms and stuff. But in reality, what entropy is a movement of energy from a useful state to a useless state. And what we have with life on Earth, of course, is we receive sunlight, white light from the sun. It arrives, it gets processed by plants and animals and light, and it gets radiated out into the universe as infrared light. So the amount of energy in equals the amount of energy out, basically. But the light, the photons, have been degraded from white light, where they have short wavelengths, to infrared, which has long wavelengths, and so the sort of usefulness of energy has decreased. And that process occurs across the universe. For everything that happens, there is a processing of energy from a useful state into a more useless state. And that happens with everything. But when we ask the question, what was the initial state of the universe, right, compared to today? The answer is that the universe must have been at very low entropy. And what I mean by that is that the entire life of the universe has been the processing of useful energy into useless energy. And it's done a lot of it, right? There's been a lot of stars, etc. So there must have been a lot of useful energy stored up in the early universe, which has become useless today and will become even more useless into the future. And the question is, where was that energy? Where was it stored? And the sort of standard picture, which is one that Penrose has been pushing, is that that energy is stored in the gravitational potential. What happened is the universe was born, matter was effectively smoothly distributed. Okay? And matter, when it's smoothly distributed and has a gravitational influence, that is a low entropy state, because that energy, which is stored in the potential, can be released as matter gets dragged together due to the action of gravity. And then that gets crushed down into stars, and then you release nuclear energy. So it was the smoothness of the universe when it started that was meant to be the place where energy was harbored. Now, the universe could not have been completely smooth, because if the universe was completely smooth at the start, it would be completely smooth today. So there must have been tiny ripples in the distribution of matter in the universe, and those tiny ripples were the seeds where matter started to flow into galaxies and into stars, etc. And there's a whole complicated process where these seeds sort of come from. But Penrose's question is why was the universe born effectively smooth, right? Why wasn't the universe born in a higher entropy state? i.e., why wasn't it born with clumps of matter? And ultimately, the question boils down to, why wasn't the universe born filled with black holes, right? Because black holes are the ultimately collapse objects, right? So their gravitational potential, if you fill the universe with black holes rather than matter, the gravitational potential is really low, because all you can do is get black holes to collide together, and that's it. So you can't release energy any other way. And so this really bothers Penrose, right? So this question of why the universe was born smooth, not completely smooth, just teeny bit away from smooth, rather than lumpy or filled with black holes, is one of those strange initial conditions for the universe. And in fact, it's got a whole sort of mythology and things around it. It's known as the past hypothesis, the idea that the universe was born very special in terms of its arrangement, such there would be lots of available energy that could be used to form stars, power generations of stars, and eventually get to planets and people, etc. And there's a nice illustration in Penrose's book. I can't remember if it's The Road to Reality or one of the other ones, where he has this picture of the divine being choosing the initial conditions for the universe in terms of the entropy. And there's a godlike figure, and it's placing a pin into the phase spaces of all possible universes, and it's picking out this tiny volume, which is like 10 to the 10 to the some huge number. That's the chances of that point being picked out. And to Penrose, this question of the initial entropy is the big question. That the other bits of fine-tuning, that's almost icing on the cake, right? Because if our universe was born with no available useful energy to use, it doesn't matter about what complexity there is, because there's no energy to drive anything. So you end up with a periodic table, but what's the point? If without a flow of energy from useful to useless, you cannot have life. I think that's like one of the most basic statements that we have. So entropy plays one of the key central roles in life in the universe, and the fact that we started at very low entropy is one of the big mysteries. And it wasn't just Penrose that this bothered, right? It bothered Boltzmann as well. So, Boltzmann didn't know that we lived in a universe with a finite start. So he didn't think that we lived in a universe that had a special start and has been evolving. So to him, he thought the universe was essentially at a state of maximum entropy everywhere. And every so often you get a statistical fluctuation of order, and that from that order you get the life of the universe. So we are on an upward trend back to maximum entropy, and we're part of this fluctuation. So it bothered Boltzmann, and it bothers people like Penrose, and it bothers me that the initial stages of the universe seemed quite special with regards to this sort of entropy picture.
David Albert, who coined this term, the past hypothesis, has been on the show a number of times, and it's been great to talk with him. But I have a question about the early conditions in the universe. And I think this idea of useful and useless energy is going to be very helpful in answering this question I'm about to pose, which is the early universe was very homogeneous, and at the same time it was very low entropy. But when entropy is typically explained, the states of very high homogeneity are the high entropy states. So when we think of an egg and an omelet, the egg is the one that's in a lower entropy state because it is quite heterogeneous, and for the given macro state, it could have a much smaller possible amount of microstates and still be indistinguishable, whereas the omelet could have far more many microstates and still look the same. So when the universe is so uniform and so homogeneous, there are so many different microstates where it would look the same, roughly. So I don't really understand where the low entropy of the early universe comes from if it has this very uniform configuration.
So the problem is that your notion of microstates, when you include gravity, it becomes different, right? So let's go back to the usual example that we have, right? And gas in a room, and if we had all the gas in one corner and we let it go, then it would fill the room, right? So when that gas, of course, is located in just the corner, it has lots of potential energy. right? In the sense that if I had that gas and it was all in a balloon, I could put a little fan on there, and as I released the gas into the room, the fan would spin. I could extract that energy as the gas fills the room. But once we get to the stage where the gas is uniform in the room, my little propeller stops spinning, right? So you need a pressure difference to extract energy in a gas, okay? So the potential is to do with going from the gas being condensed to the gas being spread out. And as you said, for gas, you look at the room, and I could rearrange the molecules in here, and they look basically the same. When you introduce gravity, though, right? So for the gas in the room, it doesn't really care about gravity at all. But once you introduce gravity and ask, where is the useful energy? And the useful energy is, right, when you have gravitation, is when particles are far apart. So if I wanted to play the same experiment, and I have, let's say I've got a big mass, and I have a paddle wheel, and I have lots of little masses spread around, and I hold that paddle wheel, then as all the little masses fall in, and they could spin up the paddle wheel, I can extract that energy as matter falls inwards, right? Once all the matter has collapsed down into a single region, then I can't extract any more of that energy again. So the useful energy, when you take into account gravity, is when everything is spread out, because the energy is released when things collapse together. Whereas for gas, the energy is released when you go from having your gas confined to having your gas spread out. So you have to do more than just look at the counting of microstates in the same way as you do with gas, because what you're talking about as well is how many ways can you clump all this material together, right? And again, of course, it all works out, but with gravity, you almost have the reverse picture of what you have with your gas. And this is why people struggle to, get a clear picture in their mind. As you said, with the early universe, matter being smoothed out should be low entropy. It should be high entropy, but only if there was no gravity, right? So if there was no gravity, then that gas would just stay there, right? It wouldn't ever clump down. But you turn on gravity, then you can start to pull things together.
That was, sorry, dog shaking his ears. That was very helpful. That's a question that's been nagging me for a long time. And that was a great answer. And I'd like to connect it back to something we spoke about a little earlier. I said I thought that the Higgs field might come in again. And what I'm wondering is, you just talked about how gravity was very important for this low entropy state. And gravity is tied to mass, and mass, as we've just talked about, is tied to the Higgs field. So when the universe was very young and uniform, my understanding, it was also very hot, and forces merge and separate at distinct temperatures. And I'm wondering if the heterogeneity that came out of the homogeneity has to do with the way that the Higgs field emerged in lowering temperatures, and whether this in turn triggered some of the gravitational collapse by giving mass to these seething particles.
Well, again, that's an interesting question. And we really are talking about the early stages of the universe here, where the physics is still somewhat uncertain. So the general kind of picture that people think is that these inner homogeneities were written into the universe during this period of inflation. So when the universe basically went through this rapid expansion due to the presence of this field called the inflaton, because physicists are rubbish at naming things. So there was this field existed for a tiny, tiny fraction of a second that caused this burst of expansion. And then after that burst of expansion, material was dumped back into the universe, right? So energy dumped in, turned into material. And from that point onwards, that's when we start to get into the, the quarks and the protons and neutrons and electrons, etc. So the inflaton is a mystery, okay? So in the same way that dark energy is a mystery today, the inflaton in the early universe is a mystery. We don't know where it came from. We don't know where it went. Now, this has led some people to suggest that dark energy is just a present-day manifestation of the inflaton, that it was there in the early universe. It's sort of hid in the background and then has come back again. And others have suggested that maybe the Higgs field is tied to all of this, that Higgs is somehow tied to the inflaton, right? So, as you said, when masses, when particles got their masses, is related to inflation, is related to matter being dumped in the universe, is related to dark energy today. So there is sort of like a patchwork picture where people have tried to suggest that these things are all tied together. The problem is with the inflaton and inflation itself, it's still very slippery. I mean, there's a billion theoretical papers on inflation, but what inflation was, what the inflaton was, what kicked it off, and how it's related to the other fields in the universe, it's still, guesswork more than anything else.
Okay, well, I'd like to come back to dark matter and dark energy, but I think while we've been on the topic, or as we're leaving the topic of entropy and initial conditions, it might be worth making this transition to the end conditions. And naturally, what happens at the end of the universe isn't, or maybe you'll disagree with me, it's not totally connected to fine-tuning in that various things could happen at the end of the universe. What matters for us right now is what's happening right now. But is there a time when life must end in the universe?
Probably. I mean, we know that. So the vast majority of stars that will ever live have been born already, right? So the rate of star formation is winding down, and in roughly a ballpark number, like 100 trillion years, I think the number is, the last star will go out, and it'll be a faint little red dwarf. It'll blink out. Universe goes into darkness. So life is going to find it hard, but not impossible, in that state of the universe. Things get really bad, though, once we get to of order 10 to the 30 years or so, because on those time scales, that's when we think protons decay. So you get out beyond 10 to the 30 years, then the stuff of matter itself will start to melt away. And the question I guess you have is what do you do? If you're a living thing and material around you is melting, then you're going to have this sort of constant need to regenerate yourself, but that requires energy. And where do you get that energy from? So there's the future is going to be this scrabbling game for trying to find the last sort of available energy to do anything, but it's all basically disappearing. And then once you're out to like 10 to the 100 years, then all the black holes evaporate as well. And they'll be the last sort of bursts of energy in the universe. Again, it would be very hard to imagine any life lasting that long to make use of that energy. But by that point, I think not that long after the last star, I think life is going to find things very difficult if it's confined to this universe, right? If it finds a way to hop to another universe, then maybe things will be fine. But if it's stuck here, then things are going to get very grim.
Now, maybe this really just totally stretches our current understanding of physics around what happens when space and time have been so stretched. But even after the last black holes have dissipated, isn't there always vanishingly low probability of Boltzmann brains or planets or solar systems or entire galaxies just spontaneously coming to existence due to quantum fluctuations or random thermal motion. Isn't it always possible?
Yeah. So we're going to end up in a universe, which was what Boltzmann was thinking about. And so, yeah, the notion that we could have Boltzmann brains, these are fully formed brains with memories, etc., pop into existence. That's somehow written onto the future life of the universe. And of course, this is one of those things that people get really tied up in a knot over, because if we are going to end up in that universe with an infinite future ahead, then there's an infinite number of possibilities to make Boltzmann brains. So the notion of consciousness over the life of the universe, the physical consciousness, as today, assuming I'm not a Boltzmann brain, is going to be a vanishingly small portion of all of the possible consciousnesses that could exist. So people have been trying to find their way out of the Boltzmann brain argument. And one way you can do that, of course, is by saying that there is not really a future which is infinite ahead, that there will be potentially a process whereby this universe comes to an end and new universes are born. Because in that distant future universe, there's still going to be dark energy. At the moment, we don't know, like, dark energy seems to be this thing. It sits through the universe. What if on immense timescales that dark energy undergoes like a quantum transition to a different energy state, releases some energy? Maybe that energy gives birth to new universes. Maybe that's part of this cycling that's part of the multiverse. So that might be one way out of the multiverse question, is that our universe, not multiverse, out of the Boltzmann brain question, is our universe will ultimately face an end. And in that end will give birth to new universes. But again, we're in the realm of science fiction and speculation here rather than hard science.
Right. I guess for the purposes of our conversation, I'm not so concerned about the problems around consciousness and whether or not we're Boltzmann brains. I just have in mind, I think it was Sean Carroll who introduced this idea that just as there could be Boltzmann brains, there could be Boltzmann planets or galaxies. I mean, they're much more complex than Boltzmann brains, so they'll be much more rare. But even well after the normal universe is dead, I mean, as physics has it now, there wouldn't really be an end to life, since it could just continuously, spontaneously emerge, although it on very rarefied timescales.
Yeah, absolutely. I mean, you do run into that problem that the Boltzmann already recognized is why is our universe so big, right? So if we are a fluctuation, why was the fluctuation so large that it's bigger than we can see? Because you don't need a universe scale fluctuation to have a Boltzmann planet or a Boltzmann galaxy, right? So you could imagine that you have a galaxy formed out of nothingness, but just beyond that, there's chaos, right? There's maximum entropy just beyond there. And maybe you can get life, etc., in that galaxy, and it doesn't see anything else out there. So I said that this is a question that bothered Boltzmann, is if we are a fluctuation, why is the fluctuation so big? Because as you said, Boltzmann planets and Boltzmann galaxies should be much more common than Boltzmann universes. So yeah, he didn't have an answer to that question.